So we're going to look at doing an FEA analysis on a floating pole conic, and we've built the conic here in MPanel, and we've added a few items to the conic since making it in MPanel. In MPanel, of course, we had a top ring here, which is coloured green, and I've added in the pole, which we're just allowing to be floating, and that's drawn as a 3D polyline. And I've also added in lines which are representing guy lines, drawn here in red, supporting the bottom of the pole. Now, we can model a conic like this with a floating pole in MPanel, but what I'm assuming here is that we've been given the shape, in other words the actual MPanel model of the white bits here, and I've had to draw the rest of this stuff in AutoCAD to be ready to analyze it in the FEA. In the FEA, we have to find some way of allowing the pole and the top ring to move up together, and we do that by specifying that by putting a tag of special data on these two polylines, that they're going to be regarded as a link structure pair. Link structure pair means that FEA will automatically build a link structure from these two items. So with those two items selected, we would set that data. You can see I already had it set from earlier, but it sets it to being a link structure pair. Just thinking about some other settings in the build model. This, of course, is a smooth surface all the way around here, so we specify it as joined edge meshes. We want to calculate the initial tension, that's the tension on the cables. MPanel will be able to calculate the initial tension on these cable edges just here. But if we, for instance, told it to do cable and guy, it might try and calculate the tension in these elements. It might think it's a guy, so it'll be safest to say just cable in there. And we're going to have to specify in the FEA what the tension is on these links, on the guys supporting the floating mast. And since we've coloured these as red, they will become in the lists section. They will become C list 1. If they were coloured yellow, they would be C list 2. If they were coloured green, they would be C list 3. So those will become C list 1. So it'll be quite useful to have on the table list extra links. Normally that's set to none, to ask for any C lists which exist to be noted in the table. So at that point we can go in, select the model, make the model, and on our build report you can see we have one region which is correct because everything is all connected in all the way around, and 105 bandwidth will solve nice and easily. Of course, we've got this lowish bandwidth by using a fairly coarse mesh. If you find that you have a high bandwidth, let's say over 200, I would recommend reducing the mesh density for the FEA analysis. Now let's have a look first and see what kind of model the FEA is actually built. I'll draw in the membrane so we have a reference point, and I'll draw in now the cables and links in the same place, and you can see that the center pole and top ring has been replaced with this TP arrangement of links and poles. So here is they're grouped together, but these are all individual links formed into that TP. And that is the method that we allow these links in here to move upwards or downwards or sideways whilst maintaining the circular shape of the top ring. If you remember the color coding that we use on cables and links, is that those links which the program has automatically calculated the initial tension for are colored cyan. The links that we need to specify the cable tension for are colored magenta. And I'll go in just for completeness and show the restraints, which are these points, which are fixed points on the frame. So now let's, with that model in mind, let's look at the actual table of links and see what it looks like. And we have the individual cable edges, 1 to 6, 7 to 12, 1 to 6 might be 1, 2, 3, 4, 5, 6 around there. So each of those is being identified and put in as our default set from up here, where we've set the default cable, the default 8mm 5/16 cable with normal behavior. The pole links, and these are the links representing the poles, that's links 43 through to 151, have had a note put on them that they are compressible, that is, they can take compression. A normal cable won't take compression. They're given a sort of a nominal EA, that's whatever the EA is in the pole setting from the defaults. Doesn't particularly matter because there are so many of them that we're not expecting them to compress any appreciable amount. And then we have our C list 1, which of course are the items that were coloured red just there. We can look at the C list. And here's C list 1, there are the item numbers, and we could draw that out if we wanted to check. So here in red are the C list numbers. When we jump over to the pre-stress, of course we need to decide what the overall pre-stress is on the structure. This is the average pre-stress in the fabric, and in MPanel FEA we will start with a rather high value and leave it to the designer to reduce as necessary. All of these edges around, go back to this one, all of these edges around here which are coloured cyan, they have their initial tensions automatically calculated, but the links which represented the pole structure and the links on C list 1, neither of those have their tensions automatically calculated. We have to supply values for them. With the links representing the pole structure, I know from experience that we can start out with an initial tension of 0 because there are so many of them that the compression that builds up in them in each individual link will be fairly low. However, on C list 1, that is the cables which are the guy cables going underneath like this, they're C list 1 because they're coloured red in the initial drawing. Those we ought to assign some kind of reasonable tension for. And we're just going to guess, and we're going to say, look, the cable tensions around on this edge are about 2,500. Perhaps the cable tensions in the cross members there also about 2,500. Of course, this depends quite a lot on the angle that the cables are coming down at and how many cables there are. The smaller the droop, in other words, if this cable went in a much smaller droop to where the line looks something like this, then we would anticipate much higher tensions. But all we're trying to do at first is get it to a point where we can solve the model, and then we will come back and refine this value here. So we'll go ahead now and solve the model for load case 0. A good quick solution. In general, you would generally get good quick solutions with MPanel FEA as long as you keep the mesh density down. And on the results, we'll start out by plotting the displaced shape. And we'll look at that in front view. And if you remember, the green is the original, and the white is the displaced shape. And you can see that with the tensions that we put in, the top ring has lifted. In other words, we've got a little bit too much tension in these cables, and so we've got a distortion of the model in load case 0. What we would do now is we would alter the pre-stress for C-list 1. We were at 2,500, and then we have a couple of methods of doing this. The simplest to understand is just to alter this this number here. Let's take it. We've had it 2,500. Let's reduce it down to 1,500. Solve again, and plot the results out again. And looking at that in front view, oops, let me get to the right drawing. We can see now that we are closer. We're moving. That the model is actually sinking down a little bit. So the top ring is sunk down a little bit. So probably a pre-stress value of 2,000 between those two would be close enough. There is an automatic way of feeding those tensions back. That's called a refine initial tensions from LC1 results, and we can ask for those to be done by requesting a refine on the AutoCalc. This is a slightly sort of more automatic way of doing it, but I don't think it's quite as intuitive. Having got the tensions correct for load case 0, we could start applying some loads for wind and snow. I have here the solutions to those. If we look in front view, here is the effect on the model with a heavy snow load, and you can see that the floating mast and the top ring have sunk down. And here is the effect on the structure with a wind suction load, and here you can see the floating top ring has come up and the mast has come up. It is important to check, especially on the uplift case, that we still have some tension left in the guys. You can see that the guy tension, which we started out, if you remember, at 2,000, and in this uplift case the guy tension here has gone down to 850. If the guy tension gets down a bit towards 0, then you can imagine that the structure is going to be in a state where it may well do some damage to itself as the uplift comes off. So in general, in the highest wind suction loads, we want to ensure that we have some tension left in those bottom guys.